Good morning again, everybody, and welcome to I lost track of what the weeks. I think we're week 7. Okay, we are still finishing chapter 37. From the get-go, there is some changes that I might make on the exams. Basically, exam 2, which is supposed to be on April 7th, which is roughly about a month from today. It's supposed to cover chapters 37, 38, 39, and 40. Here is the problem, though. Chapter 40 and 41 really are only one chapter. Both of them are dealing with Schrodinger's equation. One of them is 1D, the other one is 3D. There is tremendous difference between the one-dimensional case for quantum mechanics and more than 1D. For the hydrogen atom, for example, you're going to pick up 2 quantum numbers, okay, for the 3D. And that's where chapter 41 comes in. So chapter 41 builds on the ideas that are developed in chapter 40 and then comes up with an extension of that. So that's why I'm kind of debating whether or not to move chapter 41 to exam 2, and then we will be covering chapters 37 through 41, or leave chapter 40 to exam 3. And in that case, we will be just doing chapters 37, 38, 39, which makes then exam 3 extremely loaded because we still have to cover stuff from chapter 40 a little bit, and then also add to them the rest of the chapters, basically 5 chapters. So this is something that I'm debating, and I did not really make a decision. In either case, you will know ahead of time. And when we do the review, you will know exactly what is going to be covered in exam 2. The date should not change. It's still due on April 7th. However, if we're going to include chapter 41 with it, we may actually move this one slightly further. We may have to move it to the week after, which is the 14th. So we'll see how it goes. That is one thing. The other thing also is lab of week related to relativity, basically, that is now has been moved to, it was actually due on March 19th. That too may see some changes in the due date on it because of the fact that there are 2 essential components into that lab. The first one has to do with the stuff that we've been doing in relativity, namely the time dilation and also the simultaneity and the length contraction and all of these things. But there is another component to it that involves nuclear physics related to an item that we didn't cover from chapter 37, which hopefully we'll cover today. And then we will see how we're going to proceed with that lab too. So that is something that we may have to change the due date on that one, in a sense, push it a little bit further too. So these are the things that I wanted you guys to be aware of in terms of exam 2 and also in terms of the lab. Okay, so let me share with you the screen to see where we stopped last time. I'm hoping to get at least 2 problems today too. Okay, so let me share. Okay, so last time, if you guys remember, we came up with, first of all, these are the Lorentz transformations that we worked off of them. And they're extremely important for everything we did. Among other things, we found how the velocities add. All I did was take the deltas of all of this, assuming that the time delay between the events is delta t, and so on and so forth. And we found this expression for how the velocities add. The velocity is the velocity in the moving frame plus the relative velocity of how the frames move with respect to one another. And that's why I used u instead of v in there. And we look at the special case if, for example, v prime is equal to c. Let's say, for example, we shine a light of beam in that reference frame. How fast is going to be measured from the first reference frame? And if we do the algebra and we cancel what we need to cancel, everything is going to be c also. And that is no strange. That is not really something that is unexpected, because the theory was built on the idea that regardless of how fast referential frames are moving with respect to one another, they will always measure the same speed of light. So if you shine a light of beam in here, a laser beam with a speed c, and you know it's light in here, so the second observer must also find c. So this turned out to be actually no surprise, in a sense that if one, because the first, the observer in the moving frame will give the value of the light as being c. And if you do the algebra, according to how the velocities add using this expression, you will indeed find C. And that is why Michelson and Morley actually got that result, in a sense that no matter which way they orient their devices, they always get the same velocity no matter what. There is no interference patterns that form in the interferometer because of the difference in speeds, regardless of how fast the Earth is moving or not moving at all. So that's basically no surprise, because the whole theory was built on the idea that all inertial frames observers will measure the same speed of light regardless of how fast they're moving with respect to one another. So that's basically how that is. But this relationship is useful because it's not necessarily for light. You can use it actually for everything else. So for all speeds, you can use this expression, okay? Obviously, I didn't try the expression, but hopefully you guys caught on it. From the vantage point of the moving observer, the velocity v prime is actually going to be v minus u divided by 1 minus u over c squared v. So everything where is a v prime, where the prime was, you replace it with an m prime, and where the prime was not, you place a prime on it. And then because from vantage point of the moving frame, you are moving away in the opposite direction with the velocity negative u. That's why this expression is. If you don't believe this expression is going to turn out to be the case, use the reverse Lorentz transformations that relate, namely x prime being equals to x times gamma, of course, minus ut, and t prime being equal to gamma times t minus u over c squared times x, okay? So if you use this expression and use the deltas in a similar fashion and divide and do the simplifications that we did in here and call this one v prime and call this one delta x over delta t as being v, you're gonna end up with the same expression. So I didn't try this one because by symmetry, it's an extension of that one. It's the same as this one, but this is from the vantage point of the moving frame. This is from the vantage point of the rest frame, where you're supposed to be watching the moving frame. So both of them are equivalent. The only difference is the negative changes sign in here, and that's it. And this too will give you the same expression. So if the moving observer, if the rest observer finds that the speed is c, the other one also will find that c. I mean, you just place c in here, and this becomes c, cancel c from this c. So you will have u over c, and you will have c minus u divided by 1 over u over c, and then do the simplification in here, and end up again with c. So in either case, you're going to end up with c. So that's how the velocities add, and that's an important concept, because in classical mechanics, if the frame is moving with, let's say, 50 miles per hour, and you're jogging at 6 miles per hour, the speeds add up simply, if you're moving in the same direction as the train, as 56 miles per hour. This says this doesn't work this way. It works in this fashion, okay? So the way that the velocity is added in classical mechanics is easy. But now you have to include that term in the denominator, okay? And that's it. But the reason why it works is because most of the times 50 miles per hour is a lot less than c squared. So you don't care for it. That's why this term is negligible. You end up with a classical expression, v prime plus u, okay? So that's why it works in classical mechanics, because the speeds that we're talking about, 6 miles per hour and 50 miles per hour, they're extremely small compared to 300,000 kilometers per second, which is extremely high speed, or 200,000 miles per second. So in order to find it per hour, you have to multiply that by 3,600. So it's an extreme value, extremely small. That's why we're neglecting this term in classical mechanics, and we reduce back to the old expression that we know. Which brings me to another point that I didn't mention all along, but that's actually critical in all of this analysis. Classical mechanics was correct. And this is an important point. Old mechanics, if you want to call it that, is correct for V's that are extremely small compared to the speed of light. This is what our daily, you did the Atwood machine, you inclined plane, the vibration zone string, whatever you can think of, all of those labs, and you did measurements with the errors, and these are perfect. Why? Because you're dealing with this scenario. So this theory that we're building, relativity, or any new theory, if you wish, must contain in it all of those phenomena. In other words, you should be able to reproduce your aqueous machine, your inclined plane, your whatever experiment that you did in old mechanics, and all of those theories, whatever the centripetal motion, all of those things, they should be able to, you should be able to find them. And the way to find them is by going back into this extreme condition where the velocities are extremely small. In other words, the factor gamma, if you guys remember it, which is a scaling factor, the fudge factor, and how we drew it last time, gamma as a function of the velocity hits a wall at the speed of light, and it's for the most part 1. And then it starts to climb as you reach extreme high speeds. So this gamma in here being 1, that is the scaling factor. When we multiply something by 1, it doesn't change. So that's why classical mechanics works, because we're most of the time dealing with the speeds. And these speeds are usually extremely less than c. So that's why all of these things that you guys did in the lab and everything else seem to work. And the only reason why they work is because of this fact that the scaling factor gamma, which is, if you guys remember, is equal to 1 over square root of 1 minus beta squared, where beta is actually that ratio of v over c. So again, since this number is extremely small compared to 1, then I neglect it in front of 1, I will end up with 1 over 1. Which is 1. That's why the scaling factor was negligible for most of the phenomena that you did. That's why this expression works. And anything else actually in classical mechanics works because we're dealing with extreme small velocities. So that's one thing. The other thing also that we talked about last time was the Doppler effect. And the Doppler effect is a very important concept, okay? Here is, first of all, something that you need to remember. This is the actual frequency as measured from a non-moving frame where the source is moving toward the observer. So this is an observer measuring frequencies. He or she measures f, whereas the source is emitting at frequency f naught. When you did a Doppler effect in classical mechanics, it was actually a different value in here. It was a different ratio. It was 1 over c minus u. Now, there is a correction which adds frequency to in the numerator and actually adds a quantity, because when you divide by a smaller number, you're actually adding. So the frequency now is shifted toward higher frequencies. And if you do again the classical approach where c is extremely large in front of you, you're going to end up with the same correction. Okay. And this is exactly what we did actually in the we did the shift in frequency over f naught, and we found it to be proportional to u over c. Okay, it's small, but that's a quantity. For most observations, even in astronomy, this is a good approximation. But however, for galaxies that are at the edge of the universe, at the edge of about 13 billion years or more, this expression will not be correct anymore, because those are moving super fast. They are actually moving close to the speed of light. So you need to go back to this expression to find their actual shift, the redshift, okay? As a matter of fact, some of them seem to be moving faster than the speed of light. So you might be saying, oh, wait a minute, anything cannot move faster than the speed of light? And that's true, because actually the galaxies are not moving at all. So this is where we are, and these are the faraway galaxies. So when you calculate the redshift, which is the shift in frequency, what we're talking about in here, you will find that this shift in here corresponds to speeds that appear to be greater than c. And this seems to be in contradiction with everything we were talking about. Well, don't worry about it. This galaxy actually is not moving at all. And this, where we are, is not moving at all. It's the space between the galaxies that is stretching. And the space is not a material object. So the space as it stretches can stretch with whatever speed it wants. So that's why you will end up with redshifts that seem to give you values that are greater than the speed of light. So that's another concept that is extremely important that hopefully you guys picked up from last discussion. The reason why I'm doing this review actually a little bit is because I know we had the exam in between, and just to refresh your minds about these things, okay? The other thing that we came up with also is the time dilation and the length contraction, which are extremely important for our analysis. And the time dilation, I don't, yeah, this is the application for the mu one. This is the length contraction. Okay. So the length in the moving frame is extended by this fact, is actually contracted by this fact. Remember, gamma is always more than 1. Okay, so the length is less as measured from my vantage point. So the meter appears to be shrunk, okay, shrinking by the factor gamma, and the time seems to be extending by the factor gamma also. So if the object has only 2 seconds left, if gamma is 4, then it's going to be 8 seconds as I measure it in the inertial frame. So these are the discussions we had last time. Any questions about these things? And the example I mentioned, which is a textbook example about the mu1's lifetime, and how it's detected. Actually, you can detect it in your own household. You can build your own cloud chamber and basically detect the mu1. Does everything else make sense up to this point? Everything?
Yes.
Okay, very good.
Yes.
So, very good. So let me share again screen to build up on these concepts. And make sure we finish this chapter first. And the last part, oh man, why is this? My mouse is not moving. Trying to get to the bottom of this, okay? Okay, so let me get the regular pen now. Don't lose sight of how gamma behaves in terms of beta. As a matter of fact, there is another useful relationship that it's good to know. Since gamma is equal to 1 over square root of beta squared, typically we write it to the power 1/2. If I square this quantity, gamma squared is 1 over 1 minus beta squared. Remember, beta, it's a shortcut for V over C. Instead of writing V over C, so people in here write beta, okay? This is a typical representation of this value. So if I invert this expression, I will find 1 over gamma squared is equal to 1 minus beta squared, move beta to the other side, move gamma to this side, and all of a sudden we will find that beta squared is actually equal to 1 minus gamma squared, 1 over gamma squared, that is. So in other words, beta is equal to the square root of 1 minus 1 over gamma squared. This is a useful expression. Beta, remember, it's V over C. So this is the velocity in terms of the speed of light. The ratio is always equal to 1 minus 1 over gamma squared. It's a useful relationship to remember because you're going to need it. At some point, you're going to be asked about speeds, okay? This number now needs to be always less than 1 for material objects. I mean, unless it's a photon, which we're going to talk about in chapter 38, gamma can never be equal to 1 because, I mean, gamma can never, what am I saying in here? This number can never be negative, okay? So the square root of 1 minus 1 over square root, gamma is always more than 1. Since gamma is more than always than 1, beta must be less than 1. Okay, that's really the consequence of that. Okay, in classical mechanics, gamma is exactly equal to 1, which means that beta is extremely small, practically 0. And that's true because the velocities are extremely small compared to C. Okay, so here is where we're going to do something of magic. Okay, okay, I'm going to make this analysis and I'm going to argue for it later on. Okay, if I take a particle of mass m, okay, and moving in the x direction, obviously this particle carries with it a clock, so its speed is v equals to dx over dt. Okay, so this is the speed of the particle in its own frame. For an observer looking at it, he's at rest, then he or she starts to measure things in their own coordinates. Okay, one of the things, and I'm going to give this expression here, and I'm going to come back to it shortly. Okay, this is what the book did. Okay, outside of the scope of the book, beyond this book, that's let me go back and just to see exactly what the word they used in the book. Okay, and I really hate these kind of things to do to you guys. but that's exactly what the book says. So I'm going to follow the book initially, but then give you exactly where these things are coming from. If you look at page 1237, okay, and they spent about 1, 2, 3 paragraphs basically to argue. Here is a sentence that they use. We don't derive the correct relativistic generalization of momentum, but here is the result. Okay, open the book, page 1237, the 3rd paragraph, the 1st sentence, okay? So what they're saying in here is the momentum of the particle, and they give you a vector, which is a big problem. And I'm going to explain why that is, okay? And the vector they tell you is basically gamma times mv, okay? That's from the vantage point of the person looking at the particle. Because remember, the particle has its own v, where gamma actually has to do with the v itself. Gamma is equal to 1 over square root of 1 minus that v over c squared. So you might be tempted to say, hey, v is a vector in 3D. It has a components vx, vy, vz, and you start working with this expression. Don't. Okay, we're going to follow the rationale. We're going to find the expression for the energy, and I will try to make the case for why this works, okay? Because this vector representation drops in relativity, and we will have to adopt, and I will explain where that is coming from, the 4 vector, not the 3 component vector. You need actually an additional component to make this one work, okay? So assume this is true, okay? So the particle is moving actually in the x direction only. So v is actually the x component only. In other words, vy is equal to vz is equal to 0, okay? If that's the case, then the only momentum I'm worried about is gamma mv. That's it, okay? So this looks a little bit better. I'm at ease with this expression, honestly, because of the fact that it has no y and z component. Because if you start taking derivatives, then you have a problem, okay? Here is the thing I was talking about earlier. We know in classical mechanics, the biggest law is, can anybody remember? Tell me what is the big
equals ma?
F equals to ma, or there is another way of saying it also, F equals to, in terms of momentum,
Mass times velocity?
that's the momentum. So what is F then? Let me write it, okay? F is dp over dt. Make sense? It's the same thing. If the
And P
mass doesn't,
stands for momentum?
sorry? P
P
is the
stands for
momentum.
momentum. Okay.
Yeah, P is a classical momentum. This is classical physics now, okay? Okay? Make sense? Everybody?
Yes.
Yes. Okay, we're going to not use this expression. We're going to, this is what I was saying earlier. In the limit when v is extremely small compared to c, we should be able to recover this expression. So we're going to make it our starting point. We're going to say that F equals to this momentum, though, with respect to time. So F then, the force, is the derivative with respect to time of m gamma v. And here is a problem with this expression. Gamma also depends on v. It's not just the v. So I'm going to write it as m, which is a constant, open parentheses, the derivative of the first with respect to time, times v, plus gamma times dv over dt. This is pure calculus. This has no magic in it whatsoever. Any objections on this expression? Because remember, gamma itself depends on v. Gamma has that v squared in the denominator. Make sense?
Why didn't you multiply m by d over dt?
M is multiplying everybody. M is the momentum. This is the momentum that we're using in class. This is in relativity, okay? In classical mechanics, gamma is 1. That's why we don't write gamma in here, okay? Make sense so far?
Yes.
Yes.
Okay, so now I'm going to use the chain rule that you guys love and cherish from your class of calculus. So I'm going to leave the m outside. I'm going to write this derivative with respect to t as being the derivative of gamma with respect to v times the derivative of v with respect to t times v, don't forget this v, plus gamma times dv over dt. Any objections to this one? I know somebody put something in the chat. Okay, Natasha, are you okay now with these things so far?
Yes, I'm good.
Okay, so do you guys see that there is a dv over dt out, common factor in here?
Yes.
Yes.
Okay, I'm gonna call that A, the normal A that you guys. So this is your A, this is your A. For right now, just to simplify my writing, because it's gonna get a little bit nasty quickly, okay? So I'm gonna write this one F, then is equal to my old MA times V, this V, times d gamma with respect to V plus gamma. And I need to find what that derivative of gamma with respect to V. Remember gamma, I'm going to write it as 1 minus V squared over C squared to the negative 1/2 power. It's the same thing. I just basically so that I can do my derivative quickly. So d gamma with respect to V, drop the power, which is negative 1/2, takes the derivative of the inside, which is negative 2V over C squared, and times this factor dropped by power 1. So this will become 1 minus V squared over C squared to the power negative 1/2 minus 1. So far, so good, everybody.
Yes.
Okay, cancel that 2 1/2 and all of that negative stuff. So this thing and this thing, they cancel, and it will be left with V over C squared. This expression looks like negative or 1 minus V squared over C squared to the power negative 1/2 times 1 minus V squared over C squared to the negative 1. And this is gamma. This is our old gamma. And this is 1 over 1 minus V squared over C squared. I mean, you might be saying, and you're right, this is actually negative 3/2. A negative 3/2 is just negative 1/2 to the power 3. So this would be gamma cubed, and you're justified. But I'm going to write it this way because there is an advantage to this way of writing it. So this is gamma times gamma squared, really. This is what that expression is. So this is gamma squared, in other words, okay? Which is gamma cubed, the whole thing. But because I have a gamma already here, which I can take out, that's why I'm writing it in this fashion. So F becomes, first of all, let's not mess with MA, leave MA alone. Let's write this expression. We have V times d gamma with respect to V. And V times d gamma with respect to V is gamma times this term. So first of all, the V, don't forget the V. There is a V already in here. There is a V. Okay, times this term, which is V over C squared. So times V over C squared. Okay, times gamma, which is part of this whole thing that I wrote, times 1 over 1 minus V squared over C squared, plus this gamma. You guys see the advantage of writing it this way because I have a gamma in here and a gamma in here. Do you guys think that that gamma will come out of this expression?
Yes.
Okay, so we're going to pull it out. That's why I wrote it that way. So F equals to gamma MA, which is the old MA times the tinkering factor gamma. Okay. Let's look at this expression. The V times V is V squared over C squared divided 1 minus V squared over C squared plus 1. Because I took the gamma out. The common denominator is 1 minus V squared over C squared. I have in the numerator in here V squared over C squared, but I have to add 1 minus V squared over C squared. You guys see that V squared over C squared cancel in the numerator?
Mm-hmm.
So all we are left with is actually gamma squared, because I have 1 over 1 minus v squared over c squared, and that is gamma squared times the other gamma. So the force looks like this. Gamma cubed ma. Okay. I know I'm putting it in here, but don't remember this expression. Forget it. Because we're not going to be using it. It's just a trick, if you wish, to get us where we need to go. Okay. Here is what we need it for. Assume that the particle has moved through a lapse of time, delta t. Then in this case, the velocity is an average velocity, which is delta x over delta t. And the acceleration is actually an average acceleration, which is delta v over v, or delta v over t. Okay. And the force actually is an average force too during that lapse of time. So in other words, the particle has moved from this point to that point, where this lapse of time is t, and this is t plus delta t, and everything else shifts by the deltas. Okay. Then in this case, I'm going to define the work in this span of time as delta W. This is not a state variable again. Remember your thermodynamics. So this delta is just to represent the small, and at the end, we're going to have the full value of work, which depends on the path probably. So we cannot really write deltas, but I'm only allowed to write it in here because of the fact that I'm dealing with small quantities, okay? So this work is going to be force times displacement. This is, again, classical mechanics, okay? This is how we defined work. And work and energy should be extended with the momentum to the new theory, okay? So that's why we're using this expression here. So what I'm saying in here is, look at this expression now. The force is actually gamma cubed averaged over that span of time times m times a. And a is just delta v over delta t. So basically what this expression then looks like, it's gamma cubed m times delta v over delta t times delta x. The only reason why I wrote it this way, honestly, is so that those people who are in math majors, they don't complain, okay? And your math instructor doesn't say that we physicists don't understand, because we are the ones who invented calculus, okay? It was actually Newton who invented calculus, so it's a physicist who did that. So we're trying to say that delta x over delta t now is actually v, that average velocity. So I can shift now, because I'm just multiplying a number, dividing a number and multiplying, then I can just shift the division to the other side, and that's it. So this becomes a v, and this is delta v. And the expression now, when delta t is pushed back to the infinitesimal quantities, when delta t goes to 0, everything goes to the infinitesimal values, and delta w, the work, then becomes gamma cubed m. This becomes dv, and this is v. So that is the expression that we ended up with for the infinitesimal work for an instant dt, if you wish, okay? So now we can integrate this expression to find the energy. Remember the work energy theorem? It says that the work that the object does in going from point to point is equal to the change in the kinetic energy. This is the work kinetic energy, if you guys remember. This must be also true, because this does not depend on observers and things like that. So this, we're going to adopt it as a new principle, if you wish, of relativity. So here is the deal. We start the particle at v equal to 0, and the particle now gains a velocity v. So in here, we assume that the kinetic energy must be equal to 0, and here's some finite value of the kinetic energy, which must be this integral. That's all. That's all. So the kinetic energy then should be minus 0, if you really care, must be the integral of this dw from the starting point where v was equal to 0 to a finite value of v. So I'm going to write it again, because now we have this expression dw in terms of dv, which is gamma cubed mv dv. So this is going to be m, the integral from 0 to v of gamma cubed dv. And we're going to perform that integration. Is so far everybody with me in here and how we get into this expression for the force, which is gamma cubed m A, and A is just delta V over delta T. That's basically what it is. And then I multiplied by the displacement because we're doing all in 1D. So that's going to give me the work. Force times displacement is the work. And from here, we have this expression when we go into the limit of delta T equals to 0. So far, so good, everybody?
Yes.
Did I lose it? Okay, very good. So all I have to do now is find this integral. Because remember, gamma depends on also on V. That's why I cannot take it out of the integral. So the kinetic energy then must be equal to m, the integral from 0 to v, of v dv over square root of, or not square root, I'm sorry, 1 minus v squared over c squared to the power 3/2. Okay, here we're going to perform a change of variable, again, where beta is equal to v over c. That means that d beta is equal to dv over c. In other words, dv is equal to c d beta, and v, of course, is equal to c beta. So if I replace b by its value, v by its value, it's going to pull me a c beta. And if I replace a dv, it's going to also give me a c. So there is two c's that are going to appear immediately. And the integration, boundaries of integration, when we integrate from 0 to v, the integration over beta is going to be from 0 to v over c, that's all. Because when v equal to 0, beta is also equal to 0. So the ke then is going to give me mc squared, the integral from 0 to v over c, beta d beta over 1 minus beta squared to the power 3/2 again. Okay. Obviously, I'm going to make another change of variable, which I'm going to call, now I'm running out of letters, okay? I cannot call it u because we've been calling u something else. I cannot call it w. So can I call it alpha? I'm going to call alpha equals to 1 minus beta squared, okay? So that I can perform this integral quickly, okay? Obviously, d alpha is equal to minus 2 beta d beta, and that is the numerator. Beta d beta, and d alpha, that's going to be just minus 1/2 of d alpha, and then of course this will become just alpha to the power negative 3/2. So what I have in here for the kinetic energy is the following. First of all, the negative 1/2 coming from this substitution, negative 1/2 of mc squared, the integral. I'm going to leave the boundaries for a second right now. I'm going to fill them up. So I'm going to have an alpha to the power negative 3/2 of d alpha. Is everybody okay with the change of variable in here at the end? Because beta d beta is actually negative 1/2 of the alpha, and here is a negative 1/2, and here is the alpha. And this whole thing, 1 minus beta squared, is actually alpha to the power 3/2. I just put it up in there so that I can get this derivative quickly. Now this integral quickly. Yes?
Yes.
Yeah, that's good.
Okay, so obviously when beta is equal to 0, alpha is equal to 1. When beta is equal to beta, basically, which is v over c, alpha is equal to 1 minus v squared over c squared. Okay? So those are the boundaries of integration, just sub the values of that you have in the upper limits and the lower limit. This integral, the way we integrate, if you guys remember, we add 1. So it's going to be alpha to the negative 3/2 plus 1 divided by the new power, which is negative 3/2 plus 1. So this becomes negative 3/2 plus 1, that's negative 1/2. And this becomes negative 1/2. And the negative 1/2 in the denominator will cancel that negative 1/2. Yes?
Yes. Yes.
Okay, so we're in business then. All we have to do is plug in the boundaries and we're done. So the kinetic energy, we found it. First of all, don't forget that this negative 1/2 is going to cancel the new power that is going to come down. So it's going to be just mc squared, the boundaries of integration from 1 to 1 minus v squared over c squared. Oh, I'm sorry, what am I writing in here? Why am I writing this? I already did the integral. Just plug in alpha in here to the power 1 over square root of alpha, if you like, where it's evaluated between 1 and 1 minus v squared over c squared. In other words, we have gamma already. Okay, remember, square root of alpha is actually gamma itself. So what I have in here is mc squared times 1 over square root of 1 minus v squared over c squared. That's the upper limit, and the lower limit is just 1. This is gamma. So the kinetic energy then, Ke, is mc squared times gamma minus 1. Okay, that is the kinetic energy term. When the object was not moving, when v is equal to 0, gamma is equal to 1, because remember, 1 over square root of 1 minus 0 is just 1. So this is 1 minus 1 is 0. So indeed, the kinetic energy is 0 when the object is not moving. So here is what I'm looking at in here. Look at it carefully, this expression. It says the following. It says gamma mc squared minus mc squared, when I throw in the mc squared in there. This term depends on the velocity through that v squared over c squared and in the denominator. This term has no velocity in it. So when the object is moving, it seems like I have to use mc squared, but I have to scale it with this factor that depends on gamma. This term then seems to be the energy of the system when it's not moving. So this is, I'm going to call it the rest energy. And this term in here is the total energy now when the system is moving. So this is energy when moving. When I take the difference between these two terms, I find the kinetic energy. The actual term that we're looking for, which is a kinetic energy. So the energy itself then must be, it doesn't matter if you're moving or not, this is the energy is gamma mc squared. So this is an important result. By the way, the kinetic energy also is an important result. So the kinetic energy is gamma minus 1. What am I doing here? Gamma minus 1 times mc squared. So that too is an important result. So we found the energy, which is moving or not moving. So this is energy all the time, if you wish. And this is just the energy when it's moving, the kinetic energy when it's moving, which is the case. But I'm going to say when gamma is equal to 1, which is at rest, this will become the rest energy. So this is the rest energy. And this is the energy regardless if you're at rest or not, because that's gamma is going to dictate what value it is. And the difference between the two is the energy in motion, which is the kinetic energy. So that's basically what we have found, okay? This is one way of expressing the energy. There is another way of expressing the energy. Remember, my starting point was that the momentum was equal to gamma mv. So this was the momentum. What I can do also is come back to this expression and square it. Let me explain what's going to happen when I square it. E squared is going to be gamma squared m squared c squared. C to the power 4, I'm sorry, because I already have square in here. So all I did was square the energy. Square this expression. So this squared the previous expression, okay? Gamma squared then can be written as follows. First of all, I have mc squared, mc to the m squared c to the power 4, comma gamma squared, which is 1 minus b squared over c squared, okay? This one, because remember this relationship that we found, where is it? For the gamma cubed, involving the gamma cubed, where is it? This expression ended up also being gamma squared. So gamma squared is equal to b squared over c squared over 1 minus v squared over c squared plus 1. So let me write that, that expression for gamma squared that we have derived. In other words, this is gamma squared. And gamma squared, if you guys remember, we found it earlier to be v squared over c squared over 1 minus v squared over c squared, which is gamma squared again, plus 1. This is what we have found here. Where is it? Here, this part. Okay. If you don't believe me, just do the common denominator. The common denominator again is 1 minus v squared over c squared, and you will have 1 minus v squared over c squared plus v squared over c squared. They cancel, and you end up with gamma squared, which is again 1 minus v squared over c squared in the denominator. Does everybody agree that this is an identity?
Yes.
Okay. This is true regardless of what v is. It's always true because you just common denominator and you end up with this expression. The reason why it's useful to write it that way is because I can identify terms in it. So let me go back into the expression of the energy. So E squared is mc squared squared. Or let's leave it the way it was, okay? Let's leave it the way it is. Namely m squared c to the power 4 times the first term, which is v squared over c squared over 1 minus v squared over c squared plus 1. Okay, basically all I did was rewrite gamma squared, which is this term, in terms of this expression that involves v squared and 1. Okay, obviously the reason why I'm doing this is because I left this one in here in purpose, because I have c to the power 4 and I have c squared. So one of them is gone. So this is how the expression would look like now. So e squared is going to be the first term, m squared, v squared, and c squared, divided by 1 minus v squared over c squared, plus all I'm left with mc squared squared, because I multiplied this one by 1. Okay, so that's the term. Well, if you look at the expression for the momentum was gamma mv. If I square this expression, this becomes m squared, here is m squared, v squared, divided by gamma times gamma squared, and gamma squared is 1 minus v squared over c squared. In other words, this whole thing in here is just the momentum squared, that's all. This term. Obviously, I'm multiplying it by c now, it's squared. So the entire expression for the energy then becomes p squared c squared plus mc squared squared. That is how the energy also can be expressed in terms of the momentum. So again, this is the total energy. This part is at rest. And this is the contribution from the motion. Okay. Everything in brackets in here are important stuff, is important stuff. So hopefully you guys have no problem with this expression. Any questions about how I got this one? I mean, it sounds like I did kind of an arm twisting things in here, and probably you're right, okay, to get this expression, because it's a useful expression that we will need. Any objections before I do an example now from the book, a problem from the book, not an example? Sounds good, everybody?
Yep, sounds good.
Okay, so this is basically the expression of the energy in terms of the momentum. This too is the expression of the energy all the time, which is true for this case too. This is the kinetic energy. So anytime you're asked about the kinetic energy is gamma minus 1. And this is the momentum. We hardly use it this way. So don't take too much it into this way. And the force, like I said, just a middle step. I'm going to try down the road to give you a better way of doing this thing by introducing the 4 vector. And there is a reason for doing the 4 vector, and that is because of the Minkowski basically space-time plane and 4-dimensional basically plane space, okay, whatever you want to call it, not 3-dimensional space. And you will see that actually it doesn't require any integrations or derivations or backward stuff and everything, and you end up with the same expression, okay, which you can resolve back to the gamma minus 1 and all of the other things, okay? So it's actually a much easier way of doing things. But before I do that, let me dive into example, not example, I'm doing problem 38. on page 1249. Okay. Obviously, I'm using only the 15th edition. That's the only one that we're recommending. At some point, we were saying 14th edition, but I hope that nobody has the 14th edition because I don't know. Some problems have been removed and others added. So, okay. So problem 38. It says creating a particle, 2 protons, each with rest mass m. They gave you the symbol or the capital value for it, 1.67 times 10 to the negative 27 kilograms. That is a mass of a proton, okay? Are initially moving with equal speeds, so both of them have the same speed, v, in opposite directions, so it doesn't matter when you square it, it's going to be v squared. So they usually come in an accelerator, and they are actually moving in the same direction. And at some point, the beams, they get split and then they collide, okay? So they're coming with the same speed, okay? Because they went through the same accelerator. They were ionized from the same material, from the same hydrogen, basically, gas that you have built up, and then they go through the same accelerator. So this is not strange, okay? So the protons continue to exist after the collision that also produces an eta particle, eta naught particle. Okay. See chapter 44. If you open the book, and you have the book, hopefully you guys open with you, and you go to chapter 44, you're going to see the types of, it's a meson actually, the eta particle. And like a proton, which is actually a hadron. Hold on. Where is the thing? I have to find the standard model. Okay, baryon. Yeah, both of them are hadrons. Okay, if you look at page 1496, okay, that's the page from chapter 4, on table 44.3, you will see that the hadrons are divided into 2. There are mesons, which are made up of 2 quarks. And then there are the baryons that are made up of 3 quarks, okay? So in this case, the eta particle can be made up of an up and anti-up, or a down and anti-down, or a strange with strange and anti-strange, basically quark, okay? So that's basically what it is. At this point, we really don't care about this quark stuff, but at some point in chapter 44, we really need to understand what they're talking about. But at this point, the rest mass is 9.7 for this particle, 9.7, 5, 10 to the negative 28 kilograms. Obviously, it's made up of 2 quarks, so it must be lighter, okay, of the same type, okay? So this is slightly lighter than the protons. So 2 protons, they meet together, and they produce an eta particle. If the 2 protons and the eta particle are all at rest after the collision, find the initial speed of the protons expressed as a fraction of the speed of light. So here is the deal. You have 2 particles of protons, proton and proton, coming with the velocity v. Both of them have the same speed, okay? And they collide, and after they collide, they produce an eta particle in here, and all of them, their final velocities are equal to 0. All of them, regardless of the particle, okay? Whether you're talking about the eta or the 2 protons. So in this case, what they want is gamma. Oh, I'm sorry, what they want is actually v, this question. So what we do in this case is, the final energy, because it's all at rest, all particles at rest after collision. So their energy then is just the 2 times the mass of the proton times the speed squared of light. So this is for the protons. Each one of them has a mass m, and has a speed c. So it must have a rest mass, which is mc squared, but you have two of them, plus the eta particle, which is simply m times c squared. So this is the final energy, total energy of the system. How much was it before the collision? Before the collision, you had, this has a rest mass. No, I'm sorry, it did not even exist. So before the collision, we didn't have an eta particle. It was only formed after the collision. Okay, so we don't have an eta particle, but we have two protons moving with their velocities, so their energies, so the E initial must be equal to gamma times 2, because we have two of them. Each one of them has the same velocity, times m times big M, I'm sorry, because we're using the mc squared. Okay, let me explain where that is coming from, okay? It's coming from this expression. That is the total energy, but I have big M now because that's the protons. They gave them the mass M. And each one of them has the same gamma because they're moving with the same speed. They have the same V squared. It doesn't matter which direction you're moving. And C is C. Nobody is gonna tinker around with C. So this is the energy before the collision. And this is the energy after the collision. Since the energy must be conserved, I'm going to say in this case that 2 times the mass of the proton squared plus mc squared, because they don't move after that. So there is no gamma factor in here involved. But before, the two protons were moving and there was no eta particle. The eta particle was formed because of the collision. So obviously c squared cancels. Okay. And furthermore, I'm going to divide by 2m. So the 2m also cancels from this term, and I will be left with 1 in here, plus m over 2 big M. This must be gamma. Remember, the mass of the eta particle is 9.75 times 10 to the negative 28 kilogram. The mass of the proton, I have two of them, 1.67 times 10 to the negative 27. Cancel this. With this, I'm left with a negative 1 in here. So basically, gamma is equal to 1 plus 0.975 divided by 2 times 1.67. Can anybody tell me what this number is? Quickly, please. Finish the algebra.
I got gamma as 1.292.
Okay, this is part of the discussion. I really want you guys to finish this problem in here. So what did you find, 1.29?
Yeah, 1.29.
Is there a third digit or a fourth digit?
Oh, 1.292.
Okay, the reason why I need 3 sig figs, because all of these problems have 3 sig figs in them, okay? No, that's actually enough. 1.29 is good enough. Okay, so 1.29 is good enough. Okay, here is the deal though, because we want to find V. So for that, there is an expression that I wrote today for you guys relating beta to gamma. Where is beta and gamma? This was from the beginning, actually. Here, beta is equal to 1 minus 1 over gamma squared under square root, and that is V over C. So V over C, since we find gamma, that's most of the problems, by the way, in this chapter is finding gamma or something, and then you can find V over C. So V over C, which is beta, is the square root of 1 minus 1 over gamma squared. Obviously, this is not a big enough value compared to 1, but it's still big enough to give me a significant value in here. So you're going to find from here V in terms of C. Okay, so if the two proton, so you're going to find it as an expression of C, as a ratio of C. So you're going to find the square root, basically. So that's basically what you're supposed to finish in here. So 1 minus 1 over 1.292 squared. Under the square root. you're going to find a number that is between 0 and 1. Cannot be more than, it has to be more than 0 because they have to be moving to begin with. They must have some kinetic energy to begin with. And it has to be less than 1 because it cannot be greater than the speed of light, no matter what. Sounds good? Everybody?
Yes.
Okay. But what is the kinetic energy of each proton? Well, since we found beta, we can find now what the kinetic energy is. Remember the kinetic energy, oh, since we have gamma actually, the kinetic energy itself is just gamma minus 1. Why do I always have that kind of dash in here? Gamma minus 1, what is the expression here that we found? Gamma minus 1, this expression, times mc squared, okay? And the m now is that of the protons, because we're asked for the kinetic energy of the protons. Remember, the eta particle in form don't go anywhere. So what is the rest? What is the kinetic energy of each proton? Express your answer in mega electron volt. This is important, okay? So gamma minus 1 is already 0.292 because this is correct. So this is 0.292. Please verify these numbers, okay? Don't take it. Don't take it for its face value. Times the mass of the proton, which is 1.67 times 10 to the negative 27 kilograms, times c squared. T squared is 3 times 10 to the power 8 squared. But this is in joules. We don't want it in joules. They want it in mega electron volt. So we have to convert this one into a mega electron volt. So the way we would do that is 0.292 times 1.67. Again, I'm relying on the number that one of you guys have provided. So hopefully everybody else would check this thing on his or her own and verify the information that we're presenting in here. 3, which is 9 times 10 to the power 16. That's basically what this number squared. Okay, we're going to convert from joules to electron volts. Okay. Basically, if you guys remember from your class of electricity, is that the energy can be expressed as QV, okay? If you have one electron, which is 1.602 times 10 to the negative 19 coulombs, that's the charge, times 1 volt. That is actually a coulomb times a volt is actually, so this is an electron volt, okay? So coulomb times is a joule. So this is 1.602 times 10 to the negative 19 joules. Okay. So that's what 1 electron volt is. 1 electron per 1 volt gives me 1.602 times 10 to the negative 19 joules. So in order to get rid of the joules, I have to divide by this number. Oops. 1.602. Can I get rid of that line? That seems like I crossed my calculation. So actually divide by 1.602 times 10 to the negative 19, but that gives me an electron volt. I don't want 1 electron volt. I want a mega electron volt, a MEV. A mega electron volt then is 10 to the power 6 times this number, which is 1.602 times 10 to the negative 19 joules. So this is 1 MEV. So in here, I have to multiply this number again by 10 to the power 6. And that is going to give me how many, the correct number. So 10 to the power 6 and 10 to the power 16, I'm left with 10 to the power 10. 10 to the power negative 19 and 10 to the power negative 27. That is going to give me 8, negative 8. And a negative 8 and plus 10 is going to give me a 10 to the power 2. So in other words, the answer, if everything is correct, is 100 times 0.292, which is 29.2, times 1.67 times 9, divided by 1.602 mega electron volt. Sounds good?
Yes.
You want this to the third decimal?
Yeah, the 3 decimals, yeah, 3 sig figs.
Okay.
I think that's the rationale behind leaving that 2 from the calculation of one of you guys. because then we have 3 sig figs. Okay, if we left it 0, then it looks like it's 29.0. Okay, which might increase the error. Okay, so that's probably the wisdom, because we are dealing with gamma -1 for most of the time. So if we take gamma to be 1.29, we're going to run the risk of when subtract 1 to only have 2 sig figs. Okay, we need 3. So that's why probably retain gamma up to the 4th digit in here. Sounds good?
Yep.
Okay, so if we do that, then somebody is going to give me a number in here, and you guys are going to post this one. So you're going to finish this one. So this is the kinetic energy of each proton. Okay. So part C, what is the rest energy of the eta particle? The rest energy of the eta particle is just mc squared. So E sub eta is going to be simply equal to m times c squared. Remember, the mass is given to us. And again, it has to be probably in mega electron volts because of the same requirement in MeV too. So we're going to take the mass of this particle, which is 9.75 times 10 to the negative 28 kilograms, times c squared, which is 9 times 10 to the power 16, divided by 10 to the power 6, because we want it in MeV, 1.602 times 10 to the negative 19. Obviously, 10 to the power 6 and 10 to the power 16 is 10. 10 to the negative 19 and 28, that's 10 to the negative 9. 10 to the negative 9 and 10 to the power 10, that's going to give me a 10 only. So the answer should be E of the eta particle is going to be, again, 10 times this number is going to be 97.5 times 9 divided by 1.602. That's it in MeV. Okay, mega electron volts. Discuss the relationship between the two parts B and C. How is this number of the eta particle is related to the kinetic energy of each of these protons? In other words, is the energy of creating an eta particle equal to, that's a question mark, of the kinetic energy that produced it, which is the sum of the two particles, because both of them are moving with the same velocity. So in this case, the kinetic energy of the protons, doesn't matter which one you take, you multiply it by 2, you find that this is the kinetic energy that both of them have brought up, okay? In other words, did the nuclear accelerator give them enough speed to create an eta particle or not, okay? So that is really the question. So because this energy must at least be equal to this kinetic energy if there are no losses, and if there are no losses, of course, in the system. If there are losses in the system, you need more energy to produce an eta particle. Make sense? Okay, so this is a good problem to talk about. Since we still have time, I was going to do problem 44, but I promised to come back to it on Thursday. But let me go back to that lingering point, because I really hate leaving stuff unanswered. Okay. So we're going to do 44. We're going to do other problems. Let me go back into the expression that I was talking about in here. This stuff in here, especially this one in here, that seems to just basically put it out of nowhere. What is it? For the momentum, okay? P equal to gamma mv. And we used that to derive everything that followed from it. And everything is correct, by the way. Everything we derived is correct in terms of the energy, in terms of stuff, but force and work and things like that, you have to be careful with these things. So let me explain where this thing is coming from. Hopefully we have enough time to have this discussion quickly. And you need the Minkowski space anyway for the lab. Okay. Let me explain what we're talking about now. In classical mechanics, a particle is defined by the vector r, which has components x, y, and z. Okay, that's in space, in Cartesian coordinate system. That's a vector, three vector. if you want to find the length of R, usually take the square root of its x component squared plus its y component squared plus its z component squared. In other words, you take R times R, and you take the square root of this dot product, okay? So this is the length of R. So this is called a metric. In other words, how to measure lengths, basically. If you vector changes by an amount in space, it's going to be dx, dy, dz. In such a way, the metric now for dr, the length of dr, if you wish, is going to be equal to the square root of dx squared plus dy squared plus dz squared. And this is nothing but the Pythagorean theorem, really, okay? Because this is some, in 3D, of course, it's going to look like it's a triangle of a triangle, but at the end, its length square is just square root of, I mean, it's going to be just the length, sum of these things. This is the Pythagorean theorem. I don't know if I'm saying it right or not, but I grew up in saying Pythagorean. Anyway, the point being in here is this is the length. Does this ring a bell to you guys from your class when you did geometry?
Yes.
Okay, when I did vectors, actually, if you look at your book on the chapter that you guys did, vectors. Okay, do you guys remember which chapter that is? You remember it? It's chapter 3. That's when the vectors were introduced. You did that in physics 1, didn't you? Yes.
Probably.
You guys remember?
No,
Probably.
don't remember.
Anybody else who can remember? Better memory than some of you?
Nah, not really.
Okay. That's actually should be the first few lessons that you did in physics, and it's a vectors. Okay, I don't see the problem in here, but there is a typical problem that I assigned as a homework when I was doing physics 1, because it's critical. Okay, let me tell you what the problem is. Okay, you can find it quickly in here, but let me tell you what the problem does. If you take a vector, it doesn't matter. This is a vector. Okay, if you take a vector and this is its length. Okay, it's the length of the vector, which is what we're writing in here. Okay, if I change orientation, if I look at it this way, does the length change?
No.
So in the rotation, a vector does not change its length. Its magnitude is always the same. That is actually the definition of a vector. The vector is any quantity that does not change magnitude when you do a rotation on it. Okay, so that is basically the transformation that conserves lengths. So in that case, the vector is invariant in the rotations. That's why we call vectors in some sort of an O3 space, because it does not change in the rotations. Okay, now here is the deal. This length does not stay the same. Let's take dy equals to 0 and dz equal to 0. We're dealing just with the one-dimensional again. Okay, so we're doing with the one-dimensional problem. So the length is actually dx squared. This quantity, it changes in their Lorentz transformations. I mean, it's quickly clear, because if I go from one frame to another frame, dx is no longer the same. As a matter of fact, there is a temporal component that comes in. Dx, if you guys remember, has in it gamma times dx prime minus or plus u over c squared dt prime. So in other words, this quantity is no longer just gamma times dx prime. There is a time that comes in. So the time seems to be involved in this expression. So I cannot really say that a quantity like this one is invariant in the Lorentz transformation, because it's not. It changes because there is a new component that comes in. So now the reason why it worked in the old mechanics is because dt is universal. It's everywhere the same. So it does not matter. So that's why it did not interfere with those transformations, and classical mechanics works. Now, the reason why we have to now extend this space to now another component, add a new component to this whole thing, and that is time. So time now needs to be added. So we cannot really talk about x, y, and z are only the components of a vector. I have to include in it the time t. So this is, I'm going to leave space in here. So this is really the new way of describing vectors. So we have to really add another component, because if something changes with X, if one moving frame with the other one, not only the spatial component change, but also the temporal component change. Tem is not universal anymore. To make things work in terms of dimensions, so that this is fine, because this is in meters, this is in meters, this is in meters. We really need this one also in meters. It's in seconds right now. So one way to do it is scale it by the factor c. And if we do it that way, then also this one is in meters. So now space is no longer 3D. There is a space-time. And for the lab purpose and everywhere else, actually, space is the X component in this case, because we're dealing with one dimensional, and then the Y is the T component. So in this case, even when the particle is moving in only one direction, I have two components. I have a two-dimensional space in this case, which is extended with the time. So this becomes a CT. This is the Minkowski representation that we talked about last time when we talked about the future and the past and absolute future. Did we talk about the absolute future and absolute past? I think we did. Yes, no? I don't remember this discussion. But anyway, it's going to derive from this whole discussion anyway, okay? So now we have a 4-vector. So this is a 4-vector position. Okay. We're going to extend. So everything was in here. So the metric now needs to change. Let me tell you right away what the quantity that does not change under this transformation. Negative c squared t squared plus d plus x squared. This is the quantity that does not change under Lorentz transformation. So in other words, dx squared is equal to minus c squared dt squared plus dx squared does not change. Obviously, if I include the y and the z, this is how it looks like. I'm going to put this both of them as 0 to make the whole thing easy. If we do that, then Lorentz transformation become equal to x prime or dx. Let's leave it with the x prime for right now, and then so x prime is going to be related to gamma times x plus ut, and t prime is going to be equal to gamma times t plus u over c squared times x. Okay, multiply this by c, multiply this by c, and get rid of this c, and we're back in business now, okay? So we're using the same dimensions everywhere. If you take this quantity with a negative sign and add to it this quantity with a positive sign, you're going to find it equal to the same thing on the other side. In other words, negative ct prime squared, well, the whole thing squared, plus x prime squared is equal to, it's going to be negative c squared t squared plus x squared, okay? If you use the d's, it's going to be the same. And there is no gamma that's going to appear. The two quantities are identical. So in this case, it's invariant in the Lorentz transformation, and this is a way of defining vectors. So now the vector is not defined as we did in classical mechanics, but it's defined in such a way that it observes Lorentz transformations. If it does, this is an extension of the vector that we know it in 3D. So this is a 4D vector. So if we do the same rationale for the momentum, this is how the momentum would look like now, okay? We're going to look for a momentum that does conserve, that is also conserved under the Lorentz transformation. I'm going to assume also motion in 1D, so there is only the x component and the y and z components are both of them 0, and I need a quantity in such a way that the whole thing is invariant under Lorentz transformation. That quantity turned out to be E over c, okay? So this will become my 4 momentum vector, 4 vector momentum. I'm refraining from using the symbols because honestly, the symbol for it is p mu, where mu in here has this index for this different values, 0 for the temporal components and 1, 2, and 3 for the spatial components, okay? By the way, this is the metric now that we called it, and this is the one that defines the future, defines the past, defines all kinds of things that are related to the world timeline, okay? In the Minkowski representation. But just to go back into this point in here, okay? When a particle is not moving, that means p equals to 0. The last p, if you wish. The other two, I'm going to take them to 0 anyway. And the energy in this case is just the rest mass in this case. So that's E equal to mc squared. So the momentum is going to be mc squared over c, which is just mc, and then 0, 0, 0. So this is the momentum at rest, okay? P at rest, okay? This quantity must be conserved at all times, no matter where you are, okay? So meaning, to satisfy the Lorentz transformations and the fact that this quantity is invariant under them, the first value, which is minus this quantity squared, which is m squared c squared, must be equal to the value when the particle is moving, which is this quantity squared with a negative sign plus p squared. So it's going to be minus e squared over c squared plus p squared. That's as simple as that, okay? So this is the Lorentz transformation using the metric that I was talking about earlier in here, in the XYZ plane and t, that's the three-dimensional, four-dimensional universe. And then anything is an extension of that, like, for example, the four-vector momentum will be written in this fashion in such a way that it actually respects also the Lorentz transformation, where mc then becomes the value at rest, okay? So if I take this expression and juggle it a little bit, I'm going to reproduce the same expression that we found earlier. In other words, multiply, transform this to one side and transform the other one to the other side, and you will find e squared over c squared is equal to m squared c squared plus p squared. Multiply everywhere by c squared, and we're going to find e squared equals to m squared c to the power 4 plus p squared c squared, exactly how we found it earlier. In other words, I didn't take any derivative. The only thing is, and I know I did it quickly, is mc squared c squared plus p squared c squared. What I'm trying to say in here is the following. If we follow the geometry correctly, that of Minkowski, which we're going to need for the lab anyway, and we extend the ideas that are built on the XYZ and CT, and define the metric, and the metric is the following. Any temporal space has a minus in it, like this one, and the spatial spaces have always plus. That is how we define the metric. Why we do it that way? It's because so that it stays the same under Lorentz transformations, and that is the deal. Because Lorentz transformations are derived from the principles of the two principles of relativity. Okay, so that's equivalent to saying that this is relativity. So this quantity now is invariant under, does not change under Lorentz transformations. Instead of defining the vector as a quantity whose magnitude doesn't change under rotations, that's how we did it in chapter 3. Now we're moving in chapter 37, where we're defining the 4 vector as any quantity that does not change, its value does not change under Lorentz transformation. What is its value? This value, which is ds squared, in the case of spatial and temporal values. And in the case of momentum, it's going to be minus this quantity squared plus square of the x components, the square of the y components, and square of the z components, okay? And that gives me, if you wish, the whole deal in here. So it's going to give me purely, because we know how the value is at rest. There is no momentum at rest. The only thing is there is a rest energy, which is mc squared divided by c, so it's canceled the c, so it's going to be the rest momentum, if you want to call it that way. So mc. Then the rest 4 vector momentum, because it doesn't make sense to talk about the 3 now, the 3-dimensional space. So if that's the case, then this value doesn't change no matter how fast you're moving. So it's initially minus mc squared plus 0 squared. And at some point when you're moving, it's negative e squared over c squared plus p squared. Now it's just a matter of juggling things to find what this expression of the energy is in terms of the old momentum, if you wish. And that is exactly the same expression that we found when we did through that derivation. Okay, let me tell you this. This is actually the proper way of doing it. Okay. You have to go through the 4 vectors and use Minkowski space, and the way we did it is actually because we know it's going to work, it's going to give us a result, and gave us a result. That's why I told you, forget about that value of f and trying to extend it, because you're going to find components of the velocity, components of an acceleration in the opposite direction if you really put Vy, Vz. So it does start to make no sense whatsoever. So don't extend that discussion further more than what it is. Furthermore, the book ends with the general theory of relativity. So what's going on there? In the general theory of relativity, the metric that we defined in here, which is negative the temporal value squared plus the x component squared plus the y component squared plus the z component squared, will change because this is a flat four-dimensional universe. Will change now in the presence of gravity. In other words, gravity changes that and deforms this four-dimensional space, and that is where the curvature comes into play. And that is where the extension of this theory goes to include the general theory of relativity. A big mass like the sun will make a dent in the space-time continuum, and so that the Earth is really feeling that dent, that's all. So there is no forces anymore. As a matter of fact, the force does not exist. Okay, so it's only deformations in the space-time continuum due to the presence of materials, due to the presence of gravity in this case, okay, which is the curvature of space-time continuum. And that is how we're going to analyze all of the things from that point on. That's why I told you guys, don't forget about this force. I mean, I know I wrote it and did work and all of that, and we got the correct answer because we know we're going to get the correct answer. This is the proper way of doing it. For those of you who are going to be majoring in physics, you're going to see this a lot, especially if you're going to go into theoretical physics and go into a superstring theory, because it's not just 4D there. It's 10D or 11D, depending on who you ask, which physicist you talk to, okay? If you're not majoring in any physical science, physics, and maybe even if you go to chemistry, you might encounter this stuff. Otherwise, forget about it. But you're going to need this expression that we developed in here for the homework and for the problems that we're doing. Sounds good, everybody?
Sounds good.
Okay. Everybody else?
Yeah, sounds good.
Okay. Okay, very good. So we're going to meet on Thursday, and we're going to discuss more problems, and we will see what's going to happen with the lab, okay? Let me stop the recording.